Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
I
love that word.
Hello and welcome to Diffusion. Sit back and relax while we conduct weird and wonderful science oscillating into your ears. I'm Ian Woolf. On this edition, Ramez Naam talks about exponential energy. But first up, news of cooling without power. Colder to a hotter? Physicists at the University of Zurich have been able to make heat flow from a colder object to a hotter object without using external power. The second law of thermodynamics says you can't get heat flowing from a colder to a hotter, so you wouldn't expect this result was possible. They cooled a 9-gram piece of copper from 100 degrees Celsius down to 2 degrees below room temperature. Without an external power supply, you would expect any object to only cool to room temperature. It's like ice forming on a summer day in a freezer without power. The physicists used a thermo-electric Peltier element that converts heat flow into electricity and also electricity into heat flow. The Peltier element can cool by moving the heat from the cool side of the element to the hotter side of the element when you apply an external electric current. Peltier elements generate electricity when you apply heat to one side and not to the other. Peltier elements are commonly used for small portable fridges. We need to understand some basic electronics. A resistor is an electronic component that reduces the current in an electrical circuit. An inductor is a coil of wire that converts electrical energy into magnetic energy and temporarily stores the energy in a magnetic field. A capacitor is two metal plates that convert an electric current into an electric field. Put a resistor, capacitor and inductor together in a circuit and you cause an electrical oscillation where the current changes between positive and negative, alternating current flowing forwards and then backwards. It also generates radio waves, but that's another story. Without an external power supply like a battery or mains, an oscillating circuit will conduct less and less electricity until it stops. Just like a slinky spring will bounce up and down after you release it, with smaller bounces until it stops. If you put a diode in the way of an alternating current, it only allows current to flow one way, rectifying the alternating current into a direct current. This is how your phone charger converts mains AC power to the DC power that your phone uses. The thermoelectric action of the Peltier element, converting electrical current into heat flow and then heat flow back into electric current, takes the place of the capacitor, and the Peltier element's internal resistance takes the place of the resistor. The result is that the heat flow from the hotter side causes an electric current that goes through the superconducting coil inductor and then reverses back through the circuit to reverse the Peltier element to cause cooling. And then the heat flow generates more electric current, which oscillates back to cause a bit less cooling until the energy runs out, just like the spring. The researchers have made the heat equivalent of a diode in electronics, where heat flows in one chosen direction for self-powered cooling. This experiment doesn't contradict the second law of thermodynamics because there's a loophole, an extra bit of the law that rarely rates a mention. You can't make heat flow from a colder to a hotter unless there's also some other change connected therewith occurring at the same time, which in this case you get from the changing current and magnetic fields in the circuit. The researchers only managed to lower the temperature of the copper rod from 100 degrees Celsius to 2 degrees below room temperature because commercial Peltier elements are not very efficient in converting between heat and electricity. If you knew how to make an ideal Peltier element to convert heat to electricity at maximum efficiency, in the way that a superconductor is an ideal conductor, then the theoretical maximum cooling from 100 degrees Celsius is to minus 47 degrees Celsius. More than enough for air conditioning and most refrigeration. The paper was titled Heat Flowing from Cold to Hot Without External Intervention by Using a Thermal Inductor and was published in the journal Science Advances. You're listening to Ian Woolf on Diffusion Science Radio. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com. Exponential Energy. Ramez Naam is the co-chair of Energy and Environment at the Singularity University. He's a science fiction writer, author of the Nexus trilogy, and he's an investor in clean energy startups. I began by asking him, you gave a talk at the Singularity University Australia Summit titled Exponential Energy. What does that mean?
That's right. Here in Australia, one of the sunniest places on Earth, I was talking about how technologies like solar, wind power, batteries, energy storage, electric vehicles that all used to be incredibly expensive are actually plunging in price exponentially, almost a bit like Moore's Law, and how they have now become the cheapest sources of energy and mobility in large parts of the world and are getting so cheap that it'll be cheaper to build new solar and wind than to leave an existing coal plant running.
That's a bit of a problem for an energy market that's all based around coal.
Well, it's a problem for the owners of those coal plants, and yet it's also a potential benefit for energy consumers, and certainly a benefit for the planet as well, if we can shut down those coal emissions. But literally, imagine that today, the operational cost of an already built coal plant in Australia, let's say it's 4 Australian cents a unit, a kilowatt hour. And now probably building new solar in Australia is around 3 Australian cents per kilowatt hour. So it would actually save, even though that asset owner that owns that coal plant might still owe money on it, it would actually save money to shut it down, to not operate it and build a solar plant instead. That's sort of crazy. Australia has very high retail electricity rates, but that should in the long term bring down the cost of electricity for customers in Australia too.
So if you're someone who's got a lot of capital to invest to make more money, it would be smarter for you to invest in the technology that is cheaper and more profitable rather than the old technology, but it's not where most of the established capitalists are going.
Well, if you look globally now, coal power plants, new construction has ground not quite to a halt, but I think in Asia, for instance, the number of coal plants in the pipeline dropped by a factor of 5 between like 2015 and now. And that's partially because they see this disruption coming. And if you look by just sort of capacity, peak power output, the world is now building more solar than anything else. We're still building some coal plants, especially in Southeast Asia, a few other places, but the number is dwindling because people see what's happening. So increasingly renewables dominate the new build, along with some natural gas and a little bit of nuclear in places like China and India.
I've heard people try to put across the idea that building solar panels consumes more energy than they'll produce themselves in their lifetime. Is that true?
It's a myth. The latest data suggests that in a sunny place like Australia, the total energy used to both build, transport, and install solar panels gets paid back in about a year. And those solar panels over their lifetime should produce about 25 to 30 times more energy than was used to make them.
So we've got this technology that's improving almost, or is it actually exponentially every 3 years or so?
It's an exponential. It's characterized by the learning curve or Wright's law. Every doubling of scale of solar brings down the price every 30%. It's 30% every doubling, something like that.
And we're also making more efficient solar cells and better storage systems.
Indeed, more efficient and lower cost and longer duration.
And so what is the result of the rollout of cheaper and better renewable energy?
Yeah, renewables are still quite small around the world. Wind is only a little over 4% of global global electricity, not even all energy. Solar is a little over 2% of global electricity. But deployment is sort of the trailing variable. The leading indicator is price. And most deployment until recently was just driven by policy, driven by subsidies or mandates. Now that they're so cheap, I think we're going to see that deployment accelerate quite a bit, actually.
Given that solar power and wind power the renewables are exponentially cheaper and cheaper, why do you think there keeps being a push for nuclear?
There are some places that nuclear really makes sense. We'll say a couple things. First, solar and wind are both variable, and so you can't always count on them, whether it's the day-night cycle or seasonality and so on. And so, of course, that has had people want something that is more stable. But the cost of energy storage is dropping so fast that that is alleviating a lot of the need, maybe not all of the need. I showed some data today that says that with 12 hours of energy storage, every Australian state could get to at least 90% of its electricity from solar and wind. We just have to ask, how's that last 10% going to come? And maybe that's nuclear, maybe that's even better batteries, maybe that's hydro, maybe it's some coal left on the grid. So the last bit is the hardest. That said, there are places where solar and wind are hard, places like Japan, South Korea, Taiwan, island nations that don't have a lot of sun, that are very dense. Singapore, those places. South Korea is actually the only one of them that's going big and building nuclear power plants. Japan obviously has issues still in the aftermath of Fukushima. So if you don't have a wide geographic area to build lots of solar and wind, nuclear makes a ton of sense. Aside from that, it's getting harder and harder to make the case for nuclear every day.
So how does renewable energy affect things like transport?
Yeah, so what's interesting is that as batteries have come down in price, they've also made electric vehicles a lot more plausible. The cost of lithium-ion batteries has dropped basically by a factor of 10 over this decade, since 2010. And that's a boon for people with cell phones and laptops. In fact, it started in the personal consumer tech space, and it's helped with grid storage. But the biggest consumer of lithium-ion batteries now is electric mobility. And so now what we see is if you look at an electric vehicle, it uses 1/4 the energy per kilometer that it travels, and it's about 1/4 the cost of fuel or electricity going in, and it's about 1/4 the maintenance cost per year because it just has almost no moving parts in an electric vehicle versus hundreds in an internal combustion engine vehicle, less wear and tear. So now over a 4-year timeline, it's actually cheaper to drive electric than gasoline. Okay, but consumers aren't that motivated by 4-year timelines. What's going to be upfront cheaper? It looks like by 2024, 2025, just the upfront purchase price of an equivalent electric car versus gasoline car with, let's say, a 400-kilometer range, it'll be cheaper to buy the electric. And then once you've bought it, your cost of running it is going to be 1/4 of what it was. So for ground transport, and the same is going to happen for electric delivery vans, the same is going to happen eventually for large electric trucks, semi-tractor trailers. So I think ground transport, it now looks like electric is moving into that phase of just being cheaper than burning fossil fuels.
And they have much faster recharging technology now.
It's true. We can recharge these things quickly. For most of us, most electric vehicle owners that are personal owners don't ever use a high-speed charger. You'd like to know that it's there, so if you do the long road trip, you can charge up. But people basically charge their cars like they charge their phones. They go to work, maybe they charge it there, maybe not. They come home, they plug it in, and it charges overnight, and in the morning it's fully charged, and so on. But even for things like the local delivery van, a local delivery van might go 250, 300 kilometers a day. So we have technology to just charge it overnight, and then it runs its route, and it comes home and gets charged. But for things like road caravans and road trains, as you would call them, I think, you do need to be able to charge those quickly. And so for the Tesla Semi, for instance, it looks like about an hour to get it back up to 80% charge, to be able to drive about as much as a trucker is legally allowed to drive in one day, and then charge up in an hour, maybe a little bit more than that, and that's pretty good.
Very good. I mean, it's one of the things that people worry about with electric cars is either they won't have a place to charge on the way or it'll take too long.
Yeah. I think something that's going to change a lot for personal is that today electric mobility means buying an electric vehicle. I think increasingly what's going to happen is you're going to use an app to summon a vehicle. We're all going to use more mobility services, more things like Uber, and it's going to be electric because that's the cheapest. And in fact, when self-driving cars arrive, which I think is certainly in this decade, maybe even sooner than that, maybe in the next 3 years, they're going to be almost all electric, because electric will be the cheapest. And that will, if electric mobility ultimately cuts the cost per mile by half, and if autonomy cuts the cost by mile per half, because half the cost of an Uber or Lyft is the driver's salary, you're talking about getting into maybe like a little two-seater electric autonomous pod that could be as cheap as 1/10 of the cost of a taxi today. And so then you might still own your old petrol car, then it'll sit in your garage or in your driveway and depreciate, and you'll have it for that once a month you go really far to go visit grandma or whatnot, but the day-to-day commute will be these pods or other vehicles that we summon that are electric and autonomous.
Is there any move of cargo ships towards electric? Because at the moment they use the dirtiest fuel on the planet.
Shipping and aviation are the two parts of transport that are really hard to electrify. And for both of them, we have paths to short-range vehicles being electrified. So there's tens of electric ships in the world now. They're mostly ferries and tugs that go not very far. And there's a number of companies and startups working on electric aviation for short range, for a couple hundred kilometers, a few hundred kilometers, something like that. But for long range transoceanic cargo ships and for jet aviation that crosses oceans, we really don't see a path to electrification yet. There's some hypothetical batteries that maybe someday we'll get there, but I wouldn't count on it. What's happening with ships is new regulations imposed that kick off actually in a few months here, in January 1st, 2020, are going to force them to not burn bunker fuel. Bunker fuel is basically a waste product from refineries. That's why they've been burning it, because it's almost free. So those ships are either installing filters to get rid of the sulfur emissions or buying a different fuel, or some of them are even considering conversions to natural gas or something. Hopefully in the future, we'll have totally clean fuels that we can burn in aircraft or long-range ships. And some people think it's biofuels. My personal hunch is at the pace at which solar is plunging in price, they might be solar fuels, what we call syn fuels. We use solar and wind, clean electricity to crack water into hydrogen, and then you add some carbon you've taken from the air, and you get a hydrocarbon chain, and you get a liquid fuel. You can make that a kerosene for jets. You can make it something that's more like a bunker, but cleaner for ships. And if that's the case, then Australia, as one of the sunniest places on Earth, which also has good wind, has a huge opportunity. Like the coal export market is 20% of Australia's exports right now are coal. That is going away. But the need for energy and the need for dense fuels has not gone away, just they're going to have to be clean. But Australia could turn sunlight into fuels and export them to the world.
It's a puzzling thing because we've got CSIRO developing their technology, but if you read their roadmap, they're actually talking about turning coal into hydrogen.
Yeah, so there's multiple approaches to clean hydrogen, and one approach is to take existing fossil fuel, whether it's coal or gas, and chemically get hydrogen out of it and then capture the carbon emissions that would have happened. That's one approach. And today, like methane to gas plus carbon capture, people would call that blue hydrogen, is cheaper than totally green hydrogen, which is just solar and wind to hydrogen. That's not going to last, I don't think. Carbon capture is expensive, and the cost of renewables is plunging so fast, and the cost Just as importantly, the cost of electrolyzers, the machines that turn water into H2 and O2, is also dropping fast. So my bet is that, especially in places like Australia that have an abundance of sun and wind, that totally green hydrogen made from renewables and water is going to be cheaper than that hydrogen from fossil fuels that are cracked and then have carbon capture. And ultimately, it might be cheaper than even hydrogen made from methane without carbon capture.
You have the situation in Australia where the wholesale price of power has gone negative because of the nature of the energy market, and you've even got energy suppliers complaining that there's too much power from solar. How does that make sense when you've suddenly got too much or a negative price?
Yeah. The grid is a big synchronous machine, right? And the grid, historically, until a few years ago, almost no place in the world, besides pumped hydro, had storage. So basically, energy demand and energy supply had to be matched, almost second by second, and if they were out of sync, you had real problems. Those negative prices and big price spikes will both be smoothed out by two things. One is energy storage, and energy storage has been heroically expensive in the past, and now it's getting cheap, and that will allow you, at times you have overproduction, to charge batteries, and at times you have over demand and not enough supply to discharge batteries, and that should smooth out those price discrepancies, or sort of close the arbitrage window or close the price differential over the day eventually. And the other is flexible demand. And that is underrated, actually. So if we look at electric vehicles, might be the biggest flexible demand there is. I'll tell you the stats in the US, electric vehicles would, if we electrified all ground transport, it would increase electricity demand by 50%. And just as importantly, if you have some software control of when the vehicles are charging, then you can do things like say, it's a hot sunny day, let's make sure there's chargers at work, and we're going to charge when we have the peak of solar and not enough demand. Getting towards the late afternoon as demand is high with air conditioning and solar is coming down a bit, we're not going to charge. And even if we have a wind forecast and know it's going to be a big windy night, we're going to send some economic signals, some software signals to the chargers at home and say, hold up, we think there's going to be a big spike in supply at this time, and do that smartly. And there are startups, that I know that are working on that, and markets that are being formed to do that sort of thing. Well, I would just say the future is bright, and the future is bright for Australia for many reasons. You have an educated workplace, a real market. Every modern economy has to be an ideas economy, ultimately. But the future is also bright in energy. It's not bright for coal. Coal is going to be disrupted, and it's 20% of Australia's exports today. But Australia also has the chance to export sunshine, and that can do well for Australia while doing good for the world.
Well, Ramez, thank you very much.
Thank you, Ian.
That was Ramez Naam. His other books include The Infinite Resource, The Power of Ideas on a Finite Planet, and More Than Human, Embracing the Promises of Biological Enhancement. And that's all from us this week on Diffusion. Are you a scientist, artist, biohacker or maker who'd like to be interviewed about your work? Would your company like to sponsor Diffusion? Send your contributions, opinions, helpful suggestions and donations to science@diffusionradio.com. That's science@diffusionradio.com. Please like the Diffusion Science Radio page on Facebook and rate the show on iTunes. Tell your friends. Follow me on Twitter @Ian Woolf. The news music was Rhinos Theme by Kevin MacLeod of Incompetech.com. I produce Diffusion, which is broadcast around Australia to 28 stations on the Community Radio Network, including 2RBM in the Blue Mountains of New South Wales, 8CCC in Alice Springs and Tennant Creek, 2MVR in Nambucca Valley, 3MBR in the Mallee Border districts of Victoria and South Australia. City Park Radio 7LTN in Launceston, Tasmania, 2XXFM in Canberra, and my local station 2RDJ in Burwood, New South Wales. Diffusion is syndicated globally on the National Science Foundation's Science 360 internet radio station and also on astronomy.fm. Subscribe to the podcast on the Diffusion website, www.diffusionradio.com. That's www.diffusionradio.com, and check the website for links, photos and videos about this week's show. If you enjoyed the show, you can explore more than 950 previous episodes archived on diffusionradio.com. where the shows are labelled by keywords so you can focus in on the stories you want to hear. Join my patrons at patreon.com/diffusionradio. Make a donation through paypal.me/Ian Woolf. Subscribe to the Diffusion YouTube channel at youtube.com/c/diffusionradio. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick, everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits. Photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.